Good day, everyone. We are Edan's Angels, and today we are going to discuss the continuous analytical measurement. I'm Janibel Alvarez, and with me are my groupmates, Shelo S. Estrosas and Faith Pauline Gabuya. So, for the topic overview, first topic will be presented by yours truly. It is about conductivity measurement. Second is pH measurement to be presented by Shelo S. Estrosas. And lastly, chromatography to be presented by Faith Pauline Gabuya. Now let's talk about conductivity measurement in metals, liquids, and gases. Conductivity means the ability of a material to let electricity pass through it, and it happens differently depending on whether the material is a solid metal, a liquid, or a gas. Let us start with metals. Metals are excellent conductors because they have free electrons that can move easily inside the atomic lattice. These electrons act like tiny messengers carrying electric charge. When a voltage is applied, the electrons drift from the negative pole, also known as the cathode, to the positive pole or the anode, and that flow of electrons is what we call electric current. Next, let's move to liquids. In liquids, current doesn't flow through electrons. It flows through ions. When we dissolve a salt or acid in water, it separates into positive and negative ions. So when electricity is applied, the positive ions or the cut ions move toward the negative electrode, while the negative ions or the anions move toward the positive electrode. So the more ions present, the higher the conductivity of the solution. That's why pure water, which has very few ions, is a poor conductor. But salty or acidic water conducts electricity very well. Finally, gases. Gases under normal conditions are non-conductive because their atoms are neutral or no free charges. But when a gas is exposed to very high temperature or voltage, it becomes ionized, turning into a state called plasma. In plasma, electrons are stripped from atoms and both electrons and ions can move freely, allowing current to flow. Example niya, lightning, neon signs, and arc welding, all of which involve plasma and not normal gas. So next is the dissociation and ionization of aqueous solution. First, let's start with pure water. Many people think that water conducts electricity, but in truth, pure water is a very poor conductor. It only has few natural ions, hydrogen and hydroxide, formed from a tiny splitting of water molecules. That is why kung i-test mo ang distilled water with a tester, halos wala ka gid makita nga may ma-test yung current. However, when we add electrolytes, substances like salts, acids, or bases, water becomes conductive. These electrolytes produce charged particles called ions, and ions are what carry electricity through the liquid. Now, these ions form into two ways, through dissociation and ionization. First, dissociation happens when an ionic compound, like salt, dissolves in water. The sodium and chloride ions separate naturally, and there is no chemical reaction. The water molecules just pull them apart like untangling two magnets. On the other hand, ionization happens when a covalent compound like hydrogen fluoride reacts with water. It doesn't have ions at first, but when it meets water, it forms new ions like hydrochromium and fluoride. So the main difference nila is sa dissociation, nag-split ang existing ions. While sa ionization naman, ga-create sa bagong ions through some reaction. Both will process nag-increase ang numbers ng ions sa water. That's why electrolytes make a water a good conductor. Now let us discuss the two-electrode conductivity probe, which is also known as conductivity cell. This is the most basic and traditional type of sensor used to measure conductivity, meaning how well a liquid can carry electricity. It works by using two metal electrodes placed in a solution. These electrodes are connected to an electrical circuit that applies a small alternating current or AC voltage. When this AC voltage is applied, the ions in the liquid move. Positive ions go toward the negative electrode, and negative ions move toward the positive one. This movement of ions allows electric current to flow through the liquid. The instrument then measures how much current passes and uses that to calculate the conductance, which is the inverse of resistance. So basically, if the liquid allows current to flow easily, it means there are a lot of ions, and therefore high conductivity. If the current is weak, the solution has fewer ions, meaning low conductivity. In this slide, it shows the mathematical relationship between conductance, the plate area, the plate distance, and the actual conductivity of the liquid. So the larger the electrodes means higher conductance, while farther spacing means lower conductance. Now let's move on to four electrode conductivity probes. The ordinary two-electrode design works fine for clean liquids, but in real industrial environments, electrodes get dirty or corroded. The changes that That changes the resistance and gives inaccurate readings. So the four-electrode method, or Kelvin method, solves this problem. This method, the outer pair passes a small AC current through the solution. The inner pair measures only the voltage drop caused by the liquid. Since the voltage electrodes draw almost no current, the measurement ignores any contact or wiring resistance. As a result, this method gives us high accuracy, a wider measuring range, and less effect from fouling. Some instruments even monitor their own excitation voltage to detect when electrodes get dirty. So in short, four electrode probes are the most reliable type for continuous industrial use. So the next method is electrodeless or inductive conductivity probe. This type was designed to solve one common problem, and that is electrodes getting dirty or corroded. So instead yung magamit sila metal electrodes na touch sang liquid, ang electrodeless probes naman nagagamit sa duwa ka toroidal coils sealed in a plastic body. So ang isa ka coil nagasense ang alternating magnetic field which induces a small current in the liquid. The second coil then senses that current. So the stronger the current, the higher the conductivity of the liquid.
For the second topic is all about pH measurement, and I am Shala's process, and I'll be the one to represent, discuss the information with regards to the pH measurement. So, first is what is pH measurement? In this study or in this lecture, pH measurement is defined as as a measurement that measures the hydrogen ion activity in a specific solution. This word to be used in industries because it has a strong effect on the process, especially in applications about food processing, water treatment, pharmaceuticals, steam generation on power plants, and alcohol manufacturing. For the methods of pH requirement, we have colorimetric pH measurement. The word itself, colorimetric, it uses the change of color of a litmus paper, for example, to determine the level of pH concentration of a certain solution. It could be acidic, neutral, or base. So, or the base. So, the result of the litmus paper is not exactly precise. It's just an approximation pH value of the acidity or the concentration of the solution. And we considered hydrangea flower as a natural example of colorimetric pH measurement because hydrangea flower change color with respect to the pH concentration of the soil. For example, it blooms violet when the soil is acidic. So that is one of the examples. Next, second method of pH measurement is the potentiometric pH measurement, which employs electrochemical, which is known to be special pH-sensitive electrodes inserted in a phase solution that will able to generate voltage dependent also to the pH value of the solution. So this electrochemical that is pH sensitive produces voltage based on the Nernst definition. This formula. So the voltage is equal to the gas constant, which is already given at 8.315 times the Kelvin temperature in Kelvin over the N is the number of electrons per ion. F is the current constant, which is 96,485 coulombs. And natural logarithmic C1 over C2. The C1 is the concentration of the measured solution, while the C2 is the concentration of the reference solution. So later on, we're going to discuss what is the measured solution and the reference solution. Also, we can uh, further integrate or further define this formula to its common logarithmic, which is V is equal to 0.303 RT over NF log C1 over C. So, so for example, a calculation of voltage produced by the measurement electrode for the glass is 6 pH. And for example, for the buffer solution, this example is at 7 pH. So we're going to see to the next computation. So assuming that the solution of the temperature is at 25 degrees, 25 degrees is equivalent to 298.15 Kelvin. And knowing the first equation, we're going to plug in all the values. So 208, that is 8.315 times the temperature, that is 298.15 Kelvin over 1. There's only one hydrogen ion, one mole of hydrogen ion. The product is also constant, which is 96.48. Log C1, for C1 is the measured electrode, which is the 6.0 pH mole, and then the C2 is our buffer solution pH, which is at 7 pH. And the result of the voltage is 59.17 millivolts. This table shows the following relationship between hydrogen atoms in order for the probe voltage to produce a current. And because if the impedance is too low, then the probe voltage signal will experience loaded down and will provide incorrect readings, which is not necessary or uh, which is not ideal in a system that integrates complex chemical solutions. And then modern operational amplifiers with field transistor inputs provide the required high impedance. And this circuit ensures the accurate voltage measurement from the pitch probe center. So with this kind of problem, a modern version of amplifiers is applied, which will make sure that it provides the required high impedance needed to ensure that the accurate voltage measurement of each probe assembly is correct. And when the short cables are impossible, preamplifier can be added between the each code. So here's a thing also that when the cable is getting longer, the capacitance in this cable will cause noise or interruption will affect the accuracy of the voltage. So with the use of preamplifier set at unity gain, it will use the weak voltage signal of each probe without changing its battery. So the only thing that it will do is convert the signal into a stronger but lower impedance form, which will reduce the negative effect from the 3-volt capacitance of the signal received. Voltage buffer is also a circuit which will demonstrate this preamplifier concept. So in short, this cable, the longer the cable, the high capacitance, it will reduce the negative effect of the cable capacitance. This graph shows the relationship between the float voltage and the solution pH. And as we can see that the lower buffer pH, the lower voltage it gives, while the higher buffer pH, the higher voltage it gives us. So the use of stabilization, the instrument is standard again to the second pH value. And gap between the first buffer and the second buffer is called isopotential point. And the slope of them is equivalent to 55.8 millivolts per pH.
Okay, so I'll be discussing the next topic, which is chromatography. Next slide, please. So chromatography is a vital analytical technique used in chemistry to separate and analyze mixtures. Ang chromatography is like a marathon. Ang molecules can start together, pero move at different speeds depending on their property. Some reach some finish line faster than the others, allowing us to separate them for identification or analysis. Sa chromatography, there are two main phases. Ang mobile phase, which is the fluid carrying the sample, and ang stationary phase, which is the medium inside the column. Ang chromatography method was first introduced by Michael Tuet, who used it to separate plant pigments, and the term chromatography literally means color writing. Next slide. So one simple form for high accuracy and automation. They just don't they don't just measure concentration, but rather provide an advanced analysis. And ang common applications includes determining the octane rating of gasoline and measuring the heating value of natural gas. And an example kanina, ang gas chromatography or GC. It is used for natural gas analysis. Okay, next. So in the natural gas industry, ang GC is widely used by distribution companies. It measures heating value, which serves as the basis for cost. This ensures customers to pay for the fuel's energy content and lang ang volume. The carrier gas barrels push the natural gas sample to the column for analysis. Next. Ang column is a crucial part sa GC system. For example, may column kang 20 feet long and very narrow in diameter. Actually, ang geometry and packing depende sa application. Typically, ang column is made of stainless steel and packed with an inert porous filling material, which helps separate the gas components effectively. Okay, next. Okay, GC sample valve. Ang sample valve is one of the most important components ng GC system. Ginensure ang same quantity of sample is injected during each cycle. The valve's rotating element switches between three streams. First, the sample gas stream, ang carrier gas, and the column. This maintains consistent and accurate sampling. Next. So, ang rotary sample valve has two modes, loading mode and sampling mode. Sa loading mode, the sample fills the sample loop while the excess exits to the waste port. And sa sampling mode, the carrier gas pushes the sample loop into the column for analysis. This ensures that only a controlled volume
isang sample ang gasulod sa column each time. That's the end of our presentation. Again, we are the group of Eden's Angel, and this is our report about chapter 16. Thank you.